All right, so today we're going to talk about file descriptors. I know this can trip a lot of people up when they're learning like Linux. This really applies to any sort of Unix-like operating system, but file descriptors can be a source of confusion, so I want to break them apart today. I want to deep dive into them, and I kind of want to demystify them. Now, this is going to be a long video, but I can give you the anti-clickbait version. You ready for this? So files exist in your system. They exist by name. So an example of this would be on your desktop, you might have something called file.txt. In your downloads, you might have like image.jpg. On your Unix system, you'll have /etc password. These are just files. They exist by name. When you open that file, if you have a program that opens up that file, say you want to read that file or write to that file, you're going to open up a file descriptor. So you give a path name like etc password or file.txt, and the operating system, the kernel, gives you back a file descriptor. Now, what is this thing? Well, it's nothing special. It's just an integer. It's a number. That's it. It's an integer that is unique for your process. So your process gets back an integer, let's just say 5, and that represents the open file that you have, whether that's open for reading, writing, anything like that. With those file descriptors, you can run functions on them or syscalls. I can read from that. I can write to that. I can set properties on that. The really cool part here, bear with me, is that not all file descriptors represent a physical file on the disk. Other things have file descriptors, like a device driver might be done through a file descriptor. A socket is done through a file descriptor, but you still have all the read and write and other functions like that. So the way I can read and write to a file is the exact same way I would read and write to a socket. So it's really cool. It's like one unified interface for this thing, where if you have a file descriptor, it could mean a whole bunch of different things under the hood. It might not be just a file on your disk. When we say everything on Linux is a file or everything on Unix is a file, this is typically what we mean. Technically, not everything is a file, but it's a useful abstraction. A lot of things do exist using the file abstraction. So to reiterate, a file descriptor is a number, or another way of thinking about it is a process local handle to a kernel object. You like that? I wrote that one down just because I want to remember that one. It is process local, so specific to that process. Now, when you fork and create new processes, they may or may not inherit those file descriptors, so be careful. The file descriptor could be duplicated across multiple processes. It could be duplicated within the same process. There you go. That's the anti-clickbait version. That's the very simple version. If that has captivated and interested you, then stay tuned because we're going to deep dive into all this. I'm going to show you how to create them, how to work with them, some cool tricks you can do with them, and I'm going to show you different examples. We're going to do some bash, we're going to do some C, we're going to have some fun here, so let's dive into it. So for this video, I'll be logged into my Linux system here. It's called Void. That's just the name of it. It also happens to be running Void Linux, but that's just the host name of it is Void. So let's go ahead, and the first thing we can do here is we can make dir fds. This is just for file descriptor. Nothing special about this, just an empty directory where we can do work out of for the duration of this video. So I want to show you the simplest possible example. All right, you ready? We're going to open a file descriptor, and we're going to actually read from that file, and we're going to dump it to the screen. Cat, etc password. There you go. Super simple. Now, technically, we didn't open it. We forked an exec cat, and cat did that. It read that file. It did some data. It maybe got a file descriptor back. It might be using mmap under the hood. There might be some specifics there, but long story short, cat was responsible for managing the file descriptor, which is this file under the hood. That's great. That's a super simple example. Awesome. Right. Video over. Is that it? No. We're going to write our own C program, which can handle opening a file descriptor and managing it and doing all sorts of stuff with it. So to get started, what we're going to do is we will make simple.c. And as the name suggests, it's going to be a very simple C program. So int main. Let's go ahead and be good. Let's put a nice little return down here, return 0. You technically don't need it, but I like to throw it there. I like to be specific. In previous videos, I put xxss. I decided I'm not going to do that. We're just going to leave numbers here because we're going to use these numbers later, and I'll show you what I mean with that. So let's just make sure this works. Let's cc simple output to this. There we go. Now we should have an executable. It already has the executable bit set for us. We can run it, and we have a simple C program that just exits with 0. Very simple. Let's go ahead and do something meaningful here. In order to open a file, we are going to need to use the open syscall. This is the open function that wraps the open syscall. So we can do man2 to get syscalls, and open is the name of the syscall we want here. So we're going to need the file control header, and then we have this function, open, which takes a path, some flags, and then a ... and maybe some stuff here. We'll get into that. So we're going to need a path and some flags. Now the flags are described down here. O_append, O_async, O_clo_exec. There's a whole bunch of cool flags here. We're going to do some really simple basic ones, but I'll fill you in. We'll use more as the video goes on. So let's call open, and then we can give it the path to a file. So we could do something like etc password here. All right. And then the flag that we want to give it is O_read only. This is because we don't want to write to this file. We don't even have permissions to write to this file. We just want to be able to read this file. So we can call it like this. Now we need that file control header. Luckily, I stored that in my clipboard, so that's simple enough. So let's go ahead and run this and see what happens. So if we compile that and we run it, we just get nothing because nothing meaningful actually happened here. That's because the open syscall returns data. Look, it has an int, so its return type is an int. And if we were to look for, what is it? We could probably type return here. On success, open at, and create, return the new file descriptor, a non-negative integer. On error, -1 is returned and error no is set to indicate the error. So there you go. That's what we need here. So we need to actually capture the return code of open. So we can do int fd equals open. And then we need to check if fd equal -1, then we know that there was an error and we should do something. We should just return 1 here. 1 would be that something went wrong. And we can catch this when we actually run our program. So let's go ahead and compile this. Let's run this. Let's look at our exit code. 0. We were successfully able to open etc password for reading. So we were able to open it. We got a file descriptor back. We haven't printed anything. It's not really meaningful. Let me go ahead and prove this to you by making it fail. Imagine if we went, instead of opening etc password, we wanted to open etc password, blah, blah, blah. I just hit the keyboard, doesn't even matter. So this file does not exist. There's no way this file exists. Let's go ahead and recompile, rerun it, and look at that. We have an exit error code. So there's our proof that we're able to actually successfully open the file because the file's not there. We get an error. We return 1, which is what we have right here. So let's go ahead and change this back. And now what we can do down here is we can printf, remember it's just an integer, we can printf fd equals this for an integer with a new line, and then we'll put the fd here. Now in order to get printf, I think what do we need here? Standard IO. We might need something else. I think it's just standard IO. Let's go ahead and recompile this. That worked. Run simple. And look at that. fd equals 3. So we were able to get the file descriptor as a number here. That is huge. That's awesome. So let's go ahead and be good here. We open the file here. We print the file descriptor, which represents an open file descriptor. We don't actually ever close it. Now here's the thing. Our program dies right away, so it's not a huge deal because my kernel, Linux in this example, will be responsible for closing all the file descriptors once the program exits. You don't technically have to close them the same way you don't have to free memory. You can just quit the program and you can rely on your kernel to do it. But let's go ahead and be good. Let's imagine that maybe we're nested deeply in some daemon, some program that needs to run forever. You want to be good and clean up after yourself. So we're going to need to call close on the FD. So we can do close like this. Now here's the fun thing. I think this compilation is going to fail. I think close is actually in a different header. Yeah, look at this. Close is in a different header file than open is, which is wild to me. That always blew my mind. Man2 close. You can see that is in the Unix standard header. So it's different than where open is, which is super interesting. Also, look at this. Close returns 0 on success. On error, -1 is returned and error number is set. Now, I will tell you right now, I see a lot of code out there that doesn't even bother error checking close. We're not going to bother error checking close. It's not a huge deal. We're just going to go ahead and leave it like that. We're just going to assume that we were able to successfully close the file descriptor. So let's go ahead and run this. Let's run this. Run it. There we go. FD equals 3. Okay, that's awesome. Okay, so what can we do with that file descriptor? Right now, there's a limited set of actions we can do because it represents a real file on the disk and we have it opened in read only. We can't actually mess with this file. We can't modify it, but we have it in read only, so we can call read on it. So if we do a man2read, we can pull up the man page for it and see that it's in the Unix standard header. Read is an interesting function. We've definitely used it before in this channel. As you can see, it has an S size T. So this is a signed number because it can return negative numbers, and it takes the file descriptor, a buffer to load data into, and how much data we want to read. So I'll show you what that looks like. We can also just go down here and check the return value. On success, the number of bytes read is returned. 0 indicates the end of file, and the file position is advanced by this number. That's awesome. On error, -1 is returned, and error number is set to indicate the error. So let's go back here. So let's read the file. Let's read some data from the file. We're not going to read the whole file because you have to do it in a loop, but simple enough here. We can just read some data from the file. So let's do this. We have the read syscall, which takes the file descriptor, a buffer to store the data, and the count, the number of bytes we want to read. Also, it does return data. It returns an S size T of the amount of bytes that were read. Now this is great. We have FD, but we don't have buff and we don't have count. So let's go ahead and define those here. We could say the count is, let's go ahead and read 80 bytes. Nothing special about 80. This is just completely arbitrary. And now we need to make a buffer, a character array of 80, which is the count, plus 1. We want to reserve an extra space in here so we can put a null byte so we can terminate the string so we can print it later. A little bit confusing, but this is just some C stuff. If you work with C, you've seen this before. So now we should be able to read this. I think this needs to be address of right here. So if n is less than 0, if it's any sort of negative number, then we know that there was some sort of failure. So let's just go ahead and return 1 here. And then if we've made it down here, we were able to successfully read 80 bytes into the buffer. So let's go ahead and specify the 80th member of the buffer, which is 1 beyond what we read, because remember they start at 0, it's 0 index, so we read from 0 to 79. Let's set this manually to the null byte, so we will terminate the string. And now we can do something like this. Printf read data, and then we can just put a string here of the data that we were able to read. A little bit confusing. I understand it's a little bit confusing. I'm throwing a lot of you right at the beginning, but long story short, this is the part that matters. We have that file descriptor and we're able to call read on that file descriptor. So let's make sure I can write C and I know what I'm doing. And look at this, we've read data. We have this and we have this, and that looks like the first roughly 2 lines of Etsy password. Now it does cut off a little bit because we just stop reading here. So this is probably just a little bit beyond the first 80 bytes. So we were able to successfully read 80 bytes from that file. That's huge. That's awesome. If you wanted to read the entire file, you would have to do the whole thing in a loop and read until you hit the end of the file. I'm not going to bother doing that for this example. It's outside the scope of this video, but I think this drives the point home that given the file descriptor, we can read data from it. Let's modify what we have here and let's write data to it. Now here's the thing, if we try to write data to Etsy password, it's gonna fail. So let's go ahead and write data to a file that we can modify, and for this, we're actually gonna create a new file. We'll just make myfile.txt. Now we wanna change this, we don't want it to be read only, we want it to be write only, which I think is WR only, right? You think I would have notes for this video. Is it, oh, it is, okay, awesome, I'm great. So, we open this file with write only. We also want o_bar create. So this will create the file if it doesn't exist, which is super nice. We can go here, o_bar create, and we can see if path does not exist, create it as a regular file. So that's cool, that's awesome. So if that file does not exist, we'll create it. Then we check to make sure the call to open was successful. We'll print the FD, and now we can get rid of all this read the file stuff, and then we close the FD, and we are good to go. That's super simple. So let's go ahead and just run this example. We're not doing anything with the file descriptor. We're just opening a brand new file in our directory for writing and create. So let's compile that. Let's run it. We don't have any error code. Let's ls the file. What do we have here? Okay, this is super interesting. The file exists, but why is it colored like that? That's super weird, right? If we ls-l, it looks like, what's going on here? What is this going on here? Are we like set UID? Is this a sticky bit? Like what? This is some weirdness, right? If we stat my file, what kind of permissions do we have? 4450? That doesn't seem right. So what happened here is if we go back to the open syscall, if you do man to open, you can see the open function actually takes an optional third argument. It has variadic arguments. You can specify the mode here. Now the reason it's optional is because if you're opening a file for reading, who cares what the mode of the file is? You're not modifying it. But in this example, we're creating a brand new file. We need to give it a mode. And the mode we give it, you might have seen this before, is like 755, 644, something like that. So we have to give it to an octal, 0644. It will create the file with 644, which means read write for the owner of it, read for the group that it's in, and read for everyone else. That's what we're gonna do there. So let's go ahead and back out of here. Let's delete my file. It might even yell at me because it's write protected, that's funny. If we ls, we have this, recompile the program, run the program, ls, hey, that already looks a lot better. If we ls-lh, look at this. Read, write, read, read. That's perfect. That's 644. I think if we stat the file, we should be able to see right here. Look at that. 644. Simple. All right, so we've already learned how to read from a file descriptor. Let's go ahead and write to a file descriptor. You ready for this? Very similar to read. We have the write function here, which is in the Unix standard header. It also returns an size t. It takes the file descriptor. It takes a buffer of the content to write and the size t of the count of bytes to write. It's identical to read. The only difference is instead of pulling data out of it into the buffer, we're taking data from the buffer and writing it out to the file descriptor. It also returns an SIST because it returns the number of bytes that were written, which is super nice. -1 if there were an error here. So let's go ahead and let's modify simple again. That's the binary. Let's go ahead and modify simple.c. That's probably what you guys are interested in here. So here we go. Let's go down here. Let's write to the file. So we can call write on the FD with the buffer and the count. Now the cool thing here is we can do a car star buff. I've done this in my previous video. I did this where we did hello world here, and I just counted how many bytes that was. So I would just put 11 here. This works. This totally works. There's nothing wrong with this. We will write 11 bytes to the file descriptor from hello world because HELLO space WORLD, that's 11 characters. So 11 bytes. That's what's going on there. Now in my previous video, I showed that you could do like strlen of buff, and that's totally fine. A bunch of you in the comments said that you could also do size of buff, only if I change this, because right now that will just give me the size of the pointer. We don't want that. We want this. Now you can use size of buff, right? Let's go ahead and find out. So if we do the size of operator here, it should get the length of this string. Let's go ahead and compile that, and it compiles just fine. Let's run it. Okay, it ran. Now we have that myfile.txt. If we cap myfile.txt, look at that. We have hello world. That's beautiful. There should be a new line there. Let's go ahead and just add a new line to make our life a little bit easier. We just put a new line here. The nice thing is because we're using size of, it'll automatically be accounted for. So let's go ahead, recompile this, run it, and then cap my file. And there we go. We have written to that file descriptor with a new line. And we've only written hello world in the new line, right? This is not a file descriptor thing. This is just relevant from some comments from one of my previous videos. Let's pipe this to a hex viewer. Look at this. We have hello world with 2 characters after it. I would expect 1 character, which is 0A, which is decimal 10, which is the new line or like the line feed character. But what is this? There's a null byte at the end of it. That's really interesting. We're emitting a null byte to the screen. You can't see it here, but the null byte is being emitted to the screen. The reason for that is because the size of operator is it's returning the size of the memory used by this variable. Now this string literal also has a null byte. C, because of how it is, it's a string literal here. It's storing enough space. It's actually storing, what is it, 13 bytes. It should be storing 13 bytes. 11 for hello space world, 12 because of the new line, 13 for the null byte. So we can just do size of -1 here. You do that here, you get rid of that null byte. If we recompile and then we rerun it, and then we were to cat my file and pipe it to XXD, did I do something wrong here? What did I do wrong here? Oh, wow, I forgot a flag. This is going to be an incredible learning experience. This was almost a learning experience for me. I was like, wait, hold on, I did something completely wrong. It's because in my notes, I have a flag here that I'm not using. This is really cool. Hold on, ready for this? We're gonna go, we are in a tangent and a tangent. Oh, wow, this video is, we're already pretty far in this video and I haven't even scratched the surface. All right, this is gonna be a lot of fun. I'm ready for this. Okay, hold on. Let's change this to see ya. Instead of hello world, we're gonna change it to just see ya. That's it, nothing else. Let's go ahead and recompile this, run that, and then cat my file and pipe it to XSD. See ya world. Do you see what's happening here? Oh, this is so fun. I couldn't have planned this. That's so great. I'm so happy about this. In this example up here, we wrote hello world in a new line because we wrote it with, we opened the file with write only, but all the data was still there. So we didn't actually get rid of the null byte, we just didn't overwrite it with anything. So in this example, we wrote see ya and nothing else, but that space world was already there. Hopefully that makes sense what's going on here. So if I open this back up and I change this to, let's just say hyphen, 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 5 hyphens, right? Let's go ahead and recompile this. And let's just cap my file. Don't even pipe it to the hex viewer. Just cap my file. We have the same thing because I didn't actually run the program. Let me run the program again. I should probably put these all in the same line. Run it. Look at this. Hyphen, 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 space world. And then there's a new line and a null byte there. This is huge. Hopefully this makes sense what's happening here. I'm going to show you guys what's happening here. If we run, let's do the compilation step and the running of the program on the same line. That way I won't mistake them. So if we do that, and then we cat my file. I know there's a lot going on here. We run that, we get hyphen, hyphen, hyphen world. Let's go back into simple.c and let's change that hyphen, hyphen, hyphen to underscore, underscore. Just 2 underscores, right? We rerun that. Look, see, we're overwriting the beginning, but we're not getting rid of the rest of the stuff in the file. We are not truncating the file. And the reason I use that word is because one of the flags you can open it with that I forgot, which is literally in my notes, but I forgot to pull it in here, is O underbar trunk. If the file already exists and is a regular file and the access mode allows writing, i.e. is O read write or read write only, it will be truncated to length 0. If the file is a FIFO or terminal device, the O trunk flag is ignored. Otherwise, the effective O trunk is unspecified. So this is important to us because we're opening that file and we're writing to it. We're not appending to it. That's another flag. That's O_bar append. We could do this if we wanted to, and then we would append to the file, but instead we can do O_bar trunk. So we're opening it write only, create, and trunk. If we run this now, we should just get 2 hyphens. Perfect, it got a little messed up there. We get 2 hyphens and no new line. That is beautiful, that is what we wanted. So let's go ahead and do this. Hello world with a new line. Run this, and look at that, that's beautiful. We cat my file looks like this. If we pipe it to hex dump, there should be no null byte. Perfect, because we've truncated the file. This is amazing. I normally like to put these things in my notes so we can make it into a learning experience, but that was just a legitimate oversight on my part, and I am so happy. What an amazing happy accident there to be able to show off that. I guess while I'm here, I could just show you guys that instead of O_bar trunk, we could do O_bar append. And let's go ahead and compile it. Let's just compile it. Let's run it. Let's run it, let's run it, let's run it, and then we cat my file. It shows up there a bunch of times because we've appended it and not truncated it. So yeah, that's huge. That's really funny. Oh man, I'm excited about that. All right, so there are some other things to keep track of here. Let's go ahead and change this to O_bar trunk, just so we will remove whatever's already there. We can get rid of this print here. We don't need it. We can bring it back if we need it. Right now, all this does is write hello world something to something, and it just writes to it. That's all it does. We don't actually error check this. It would be useful to error check this. So we can put an size t here of n equals write, and then we can check to make sure that the write call was successful. So let's just ensure that n equal, what we could do is count, because we know we need to write exactly that many bytes, because write returns the amount of bytes that are written. So we could do this. We could say, I think it's an size t, right? Let me double check. Man to write, the third argument is a size t. Okay. So size t of count equals size of buff. All I'm doing is taking that logic from below and putting it into its own variable. So then we can just go ahead and use that here, count here, there we go. And then we can say if n not equal to count, then we know that there was some error writing to the file, and we should return, let's just return 42 so we can detect it really easily in case this happens. So if we recompile that script, or that program, not that script, run it, we can see that we have a successful error code here, and we were able to write to myfile.txt, and that worked out perfectly. What if we weren't able to write to it? What is an example of a file that we're not going to be able to write to? There are a couple ways we could create it here. One of my favorite things about using Linux is there is this pseudo device that exists, which is beautiful. You know how there's like dev null, which you can write to and it's always successful? Actually, I'll just show it. You put dev null here, we'll be able to open it. We'll be able to write to it. Nothing will show up. That file, it doesn't actually exist. It's a pseudo file that just eats information. That's all it does. So it's completely gone there. Well, there's another pseudo device that exists that I really like. Dev full. We can open this device. But once we write to it, we will get an error. All writes will fail. It will fail as though the device that we're writing to is full. And this is super useful for testing. So if I run this, look at this. Do you see that right there? 42. We can already see the exit code because of my prompt, but we return 42. The reason we return 42 is right here. If we were not able to write it. So we tried to write to the file descriptor, it failed. We could open the file, we just couldn't write to it. So that's an example of how that could fail. Now there is more we can do here. We are just returning 42. Wouldn't it be nice if we had the error message here? We can get that. There's a nice little function called p_error, print a system error. It's from the C standard library. It comes with standard IO here. So we will need to pull in error.h. I believe we have to pull in error.h. It says it's an integer here, but it's way more complicated than that because of like multi-threaded applications. It's a whole rabbit hole in itself, but long story short, we can treat it like a nice global variable that just works. So we have a void p_error that just takes a message. I'll show you what that looks like. It's super simple. I'm gonna see if we need error.h, but I think we do. We can do pay error here and just put open. I like to put just the name of the syscall that we ran. So if there's an error here, it will print a message here. We can bring this down here and we can put a p_error for write. So let's go ahead, let's compile that. Let's see if it actually works. Okay, it works. We didn't need the error no.h. If we run this, look at this. The write syscall failed with no space left on device. That's huge. That's amazing. Isn't that great? Like this is actually a useful message and it works exactly how we expect it to work. The nice thing is if we were to change dev full to dev fully, which doesn't exist. If we were to recompile that and run it, we'll get a different message. We'll get, oh, permission denied. That's interesting. Oh yeah, we get permission denied because we're trying to create the file. That makes perfect sense. If we were to change it to try and read the file, we would get probably no entry for no such file or directory, something like that. But wow, that's really cool. All right, so let's just clean up what we have here. Dev full, perfect. And this has all been great. This is a lot of fun. I haven't even really explained what exactly a file descriptor. I told you it was a number. We've done some operations on it, but let's dive into it because have you noticed that the number started, actually, let's go ahead and print it out here. Do you remember what that number started with? Like when we open the file descriptor, cc this, run it, we get fd equals 3. Notice that it starts at 3. What happened to 1? What happened to 2? In fact, we're on computers. What happened to 0, right? Starts at 0. Well, that's the cool thing. There are automatic FDs. There are file descriptors that are given to our program that are already opened. Sometimes. But there are other file descriptors that should be given to our program. They may not be. I'll dive into that. But let's go ahead and make a new program here. Automatic FDs.c. So this is a brand new program, and we'll do something really simple. Int main. Let's go ahead and let's write to file descriptor 1. We're just hard coding this to 1, okay? We're going to write to file descriptor 1. We're going to say foo with a new line, and that is 4 bytes. That's how many bytes we want to write, so foo new line. We're going to write to file descriptor 2, and we're going to write bar with a new line there. Now, it's probably going to yell at us because we need to pull in the header for wherever write comes from. Automatic FDs. There we go. So man to write, you can see the header is the Unix standard header here. So let's go back here. Automatic FDs. Paste that in there. Beautiful. Looks good to me. Let's CC that. There we go. Let's bat automatic FDs.c just so you can see the source code of what we're running. And let's run automatic FDs. And look at that. We get foo and bar to the screen. Now, if you're confused as what's happening here, file descriptor 1 and file descriptor 2 are given to us. On a standard Unix environment, file descriptor 1 is standard out. That is our output. That is our terminal. What is here? File descriptor 2 is standard error. Standard ERR is what I'm saying, or error. And this is where this will also be the terminal. It's actually the same thing as standard out, but they can be redirected. So you may have seen this. Imagine if I were to pipe this to something like XXD, the hex dump program, right? Well, look at what happens. Bar just printed on the line. Bar didn't get sent to XXD. Bar just went to the screen just like it did before, but foo did. It got sent there and you can see FOO new line. That is the only 4 bytes that went to the hex dump there. So that's because foo went to standard out, so it can be piped. Bar went to standard error. It cannot be piped without doing some weird redirects. So let's go ahead and do it. Let's do some fun redirects here. So if we were to do something like you may have seen this, where you can do greater than dev null, this will redirect standard out to dev null. So as you can see, foo is hidden because foo went to standard out, which is file descriptor 1, but bar is shown because bar went to standard error, so it automatically goes to the terminal. Another way to write this, you could also just put the number 1 here. It's the exact same thing. We're just redirecting standard out to dev null. We could change this. We could say, I want 2 to go to dev null, and then you can see foo shows up. Foo shows up, but bar doesn't. So we've redirected standard error to dev null, but standard out, we've still let go to the terminal. Now the next thing we can do here, which is pretty cool, is we can inherit some file descriptors. So we have our automatic FDs here. Let's go ahead and modify that a little bit. Let's change this to be write to file descriptor 3, and we'll just write foo with a new line to it. Now, if you remember, file descriptor 3 was the first one that we opened up when we called the open syscall. We haven't called that yet, so what's going to happen when we run this? Well, nothing's going to happen. We haven't actually written anything. There is no file descriptor 3 in our process. We can give it one, though. Do you remember how I said file descriptors are actually kept between forks? So they are kept between forks. They may not be kept between execs. There's a special flag you can set, just like we had o underbar append. We have o underbar clo exec. Well, here's the beautiful thing. In our bash shell, we can open up file descriptors. We can run our C program, and it will have those file descriptors for us. If we were to run automatic FDs, we can see that we get nothing. That makes sense. That's cool. If we were to open up the file descriptor 3, we can open up 3 to point to where file descriptor 1 points to. If you remember, file descriptor 1 is standard out. If we run this now, look at this. We wrote to file descriptor 3, which was duplicated by bash to be our current terminal, standard out. We can rerun this as many times as we want, and it will just work how we expect it to. Once we're done with that, we can close it. You just change this to ampersand hyphen, and then we've closed file descriptor 3, and now we run it. There's nothing to write to. So that's pretty cool. You can also make this a file if you wanted to. We could say 3 goes to myfile.txt. And then if we run automatic FDs and then we cat myfile.txt, look at that. We have foo there. That's awesome. That's perfect. That's what we wanted to have. We could also write to that file descriptor too. This is outside of the program, but we can just write like echo bar to &3. And then we could even close file descriptor 3 with exact 3 greater than ampersand hyphen. And then if we cat myfile.txt, we have foo and we have bar. Foo from the C program and bar from the echo command. All right, so another thing we can do with file descriptors is we can open multiple files. We can have multiple file descriptors open in our program. So let's go ahead and make a new one. We'll call it multiple files.c. Simple C program here, int main, open and close, return 0, close it right there. We could do int fd1 equals open, and then we'll open a simple file, file1.txt, and then we'll open it with read write. Doesn't really matter here, but let's just say read write. We're going to write to it, and then o_bar create. For good measure, let's also do an o_bar trunk, just because we know what happened last time, and we'll give that 644 permissions. Okay, no trickery here. Let's go ahead and duplicate that. So now we have int fd2, and we'll change this to be file2. So we're opening file1 as fd1, file2 is fd2. Simple enough. Let's go ahead and printf those. So we can say fd1 equals %d, new line, fd1. Run this, change that to this, change that to this. There we go. Let's go ahead and write to both of those file descriptors. We can write to fd1, we can write foo with a new line, and then 4 bytes, foo new line. Same thing here, we'll write to fd2, we'll make that bar, and it will be 4 bytes. And then to be good, let's go ahead and close those. Close fd1, close fd2, and there you go, simple program. So let's go ahead and quit out of that. Let's cc multiple files, -o multiple files, like this. We're gonna get a lot of errors, right? I didn't actually pull in a lot of those files. So let's go ahead and give the includes that we need. So we'll need standard.io.h, we'll need the file control header, is it that? Is it fcntl.h? I think it is. And then the Unix standard header. So there we go, that works. If we bat multiple files.c, we can see it looks like that. If we run multiple files, we had file descriptor 3 and we had file descriptor 4. If we cat file 1, we have foo, and if we cat file 2, we have bar. Hey, that's simple enough, that makes sense. There's really no trickery going on there. Let's rearrange some of that code now. And the reason I want to do that, I'll show you why I want to do that, is because let's go ahead and group all this code together. So we'll do all the FD1 code really close to each other, and then we'll do all the FD code or FD2 code next to each other. So what happens here is we open up file1.txt, we print the file descriptor, we write the data, we close the file descriptor. Then we open up the new file, print the data, write it, close it. So we're just changing the order. We haven't changed any lines, we're just changing the order. Let's go ahead and bat that, recompile it, and run it. Look at what we have here. Notice that it is FD1 is 3 and FD2 is also 3. This is important. That means our operating system decided to reuse those file descriptor numbers. We opened up file descriptor 3, we wrote some data to it, we closed it, then we reopened a new file, so we had file descriptor 3 ready for us. Last time we used 4, now 3 was ready, so it decided to just use 3 for us. That was Linux, that was the Linux kernel deciding to do that for us. Now, let's go back, and maybe I'm gonna try and blow some minds here, but I don't actually know if I'll blow your guys' minds here. But let's undo what we did here. And so let's just rearrange code again. That's all we're doing, just rearranging code. And we're just grouping everything together. So just like we had before, it's exactly how we had before. We open the 2 files, we print the file descriptors, we write to the 2 files, and then we close them. Let's change these to just be file.txt. Notice they're the same name. This is important, okay? We're opening the same file, but multiple file descriptors to the same file. Now, this is going to be weird since we're opening the same files. We want to change trunk. I don't want to truncate the file. Let's change this to append just to make sure. But we're going to open the same file. Let's make sure, does file.txt exist? It does not exist. Cool, perfect. So let's recompile that. Let's bat it so you can see what the source code looks like, and let's run it. Let's run multiple files. There we go. File descriptor 1 is 3 and file descriptor 4, or file descriptor 2 is 4. If we cat file.txt, look at that. We have foo and we have bar. So we wrote to both file descriptors in order, and the data showed up in order. So even though they were different numbers, they're different file descriptors, they still point to the same file on the underlying file system. Now the cool thing is there's another function I haven't told you about. This function's super easy to use. Take a look at this. Instead of having to recall the same thing over again, we can just dupe file descriptor 1. There's a dupe function we can use. It just duplicates the file descriptor. It is super simple. So if you're to man dup, I say dupe, some people say dup. Look, int dup takes an old FD. That's all it does. The dupe system call allocates a new file descriptor that refers to the same open file descriptor as the old FD. So it's super duper simple. We just swap that out for dup. So if you look at it, it looks almost exactly the same. If we were to recompile the program and we were to run multiple files, we can see that file.txt will now we have it duplicated here. That's because we opened the file with append here. So we've appended a new foo and a new bar to it because we've used the dup syscall. There's another syscall we can use. You may have seen it there, which is pretty cool. There is dupe2. Dupe2 is kind of magical. It takes the old file descriptor and the new file descriptor. So this one is kind of wild. So let me show you what that looks like here. We could change this one. So we want to dupe FD1, but we want it to become file descriptor 67. We could say, we can just give it an arbitrary number here, which is huge. So if we look at the source code, you can see that we have 67 here. If we recompile it, it works just fine. And we run this, look at this, FD1 is 3 and FD2 is 67. So this is kind of huge. Think of the ramifications here. File descriptors are sparse. The numbers are sparse. They don't have to be next to each other. They can be any number you want. There's nothing inherently special about them. The kernel will try and get the lowest available file descriptor first when you allocate a new one and you don't care about what it is. But with the dupe2 syscall, we can allocate any number file descriptor we want. We can overwrite file descriptors with this. That is kind of big. So before we deal with the fact that they are sparse and the kind of implications that has, I want to show you a cool little trick we can do with dupe2. So let's call this standard out file.c, brand new program. And of course, int main, just do this, very simple. Let's do this. Let's say, not there. Int fd equals open file.txt. We'll give it o_creat, o_write only, o_append. I might actually just delete this file before we run this because that file is getting kind of big. Put a nice little 644 here. Now we will call dupe2 on fd1, and this is where we give it the file descriptor we want to duplicate over. Let's just give it 1. Do you remember what 1 is? 1 is just standard out. So let's just give it standard out here. And then let's close fd1, or fd, I just called FD1. Let's close fd because we're no longer using that file descriptor. We've just overwritten file descriptor 1. Now let's just printf, hello world. We'll capitalize it and everything. We'll put a new line. Beautiful. That's awesome. Let's go ahead and rm file.txt and let's compile standard out file. Now it's going to yell at us because I haven't actually included all the headers that it will need, but we can let it yell at us. So we need a whole bunch of stuff there. Let's go ahead and just start throwing in what we think we need. Include standard io.h, include fcntl.h, and include the Unix standard header.h. There we go. So let's recompile this. I'll pull the source code up so you guys can see it. And let's go ahead and rm file.txt. I don't even think it's there. Perfect. Let's run standard out file. We got nothing to the screen. We called printf, but we do not have anything that went to the screen. Why? Because we duplicated over standard out. So now if we were to cat file.txt, look at it there. Here it is. That's the data. It went right to the file. If we rerun the command, remember we are opening it with o_append. How do we rerun it? Like that. If we were to cat file.txt, now we have 2 lines because we're appending the data. So you can just duplicate over standard out, and then any function that writes a standard out will just go to that file instead because it's just open for the duration of that program. That is hugely powerful. Dupe is a really cool system called dupe, dupe2. There's even dupe3, I think. Really cool syscalls. Now, of course, I mentioned I was going to talk about the sparse nature of file descriptors. This kind of raises a question, doesn't it? If the file descriptors are sparse, how do we know where they are? If we're in a program and we can assume like we have file descriptor 0, 1, and 2. We've talked about 1 and 2. I haven't talked about 0. It's called standard in. You can read from it, but you can't write to it. How do we know that there aren't other file descriptors? How, when our program's running, do we know there's not other file descriptors that we could possibly use? Well, the thing is, there's no easy way to list them. Let me put an asterisk there. There's no built-in way to do them. There's no POSIX way of listing them. There's no C standard library called like list all open FDs. Like this function does not exist. but we can recreate it. There's the really easy way to do this where we can ask our operating system. With Linux, it's going to be very easy. I will show you how to do that afterwards. But for now, we're going to fake it. We're going to get our best estimate by using a little C program. And I'll show you what that looks like. There's a little function we can use called fcontrol. I've heard people call this functal or fcontrol, but file control, I've heard it called all different things. File control, functal, fcntl. I call it file control. You can give it a file descriptor and then you can give it an operation. Now the operation you give it, there's a whole bunch of stuff. There's all sorts of different things you can give it. I'll show you the one we're going to use because it's super useful. It's called getFD. Yeah, here we go. GetFT. This will give us the flags for the file descriptor. This is really cool because it will let us know if a file descriptor is valid or invalid. So we'll just call it. And then if we get a -1, we know there's an error that the file descriptor was closed. So this is going to be really, really useful for us. We can make a simple program called checkFD. That's all we're going to do here. So let's do int main return 0, close this. Now what we can do is we can give it any sort of FD. So let's just say FD3, right? Remember this one is not open by default, but we can open it if we needed to using the exec call. Let's go ahead and get the flags out of it. Int flags equals file control of FD f_ get FD. So this will get the flags for the file descriptor, and then we can just check. If flags equal -1, then we know that there was an error. The file descriptor is closed. It's invalid. Else, we know that it was working. So we could just printf here. We could say like FD is bad. Let's put a new line here. And then down here, we could say FD is good. And there you go. Simple enough. Let's go ahead and pull in some of the headers we'll need here. We'll need standard io.h because we're using printf. I don't remember where does fcontrol. It's probably in the fcontrol header, right? It's literally named after it. There you go. So we can just use the fcontrol header here. There we go. So let's bat that checkFD. Let's go ahead and compile checkFD. And let's run it. We can see that FD is bad. File descriptor 3 does not exist. We can create it though. We can do exec 3 greater than &1. So this will open up file descriptor 3, which will be file descriptor 1. It'll be standard out. If we run it again, FD is good. That's beautiful. Let's go ahead and close file descriptor 3 with this syntax. Run it again. FD is bad. So simple enough. This is a nice little way of checking, is a file descriptor valid or invalid, or in this case, open or not open. All right, so let's clean this code up a little bit. We can actually kind of turn it into a useful utility where we can loop over all of them. So we can abstract some of this logic. We can make a new function. We'll say bool, so it'll return a boolean. And of course, in order to do that, we need to include standard bool.h. There we go. So now we have booleans. FD valid. This will let us know if a file descriptor is valid or not. We'll take an FD as an argument. And then we can just simply do this. Int flags equal, let's just copy this actually. Int flags equal this, and then we can return flags not equal -1. If flags are not equal to -1, then we know that the file descriptor is valid. Otherwise, we'll return false. So true if it's valid, false if it's invalid. Now we can modify this to do this. If FD valid, FD, then we know it's good. So let's just swap these printfs around, and there we go. Very simple. Of course, we can take this file descriptor, we are hard coding it to 3, we could take it from the user. There's a couple ways we can do this, but let's go ahead and start accepting arguments. So we have argv, argc, and argv. So we can check if argz is less than 2, meaning we aren't given a single argument, then we will just print an error message. We can print it as standard error to the user, which is super nice. And we can just say usage, check, FD, and then number here. So we'll do that. We'll return 1. That way we know that there's at least one argument. We're going to use a to I here. There's some issues with it. It's not the most safe function you can use, but we'll do a to I on argv1. Very, very simple command. This will turn the first argument into a number. If anything goes wrong, I think it'll get treated like 0, but we're going to assume that the person calling us is giving us valid information. So instead of FD is good and FD is bad, we could print this. We could do printf fd%d : space. And that will be the file descriptor here. And then we can just printf good new line or bad new line. There we go. So it might be a little bit confusing. Let's go ahead and make sure that actually just compiles. We need a to I, of course. That is in the standard lib.h. So checkfd.c. Let's go ahead and pull that in here, standard lib.h. Let's compile that. Bat checkfd.c, just so you guys can see what the source code looks like. Oh, it's gonna be page. It's a little bit too long for the terminal. That's okay. Checkfd on 0. FD0 is good. That means it's open. FD1 is good. That means it's open. 2 is good. That means it's open. 3 is bad. 4 is bad. 5 is bad. That means it's closed. That's good. That's what we wanted. Of course, I could also just make this a little bit easier by changing good to open and bad to closed. There we go. And now that we have this program, we could loop over every single FD and check them. We could do something like for I in 0.1024. This is an arbitrary number. I'll explain this more later, but we could do check FD on I like this and done. And there you go. So it'll loop over all of them. If we do a control F for open, we can see that 0, 1, and 2 were open. Those were the only 3 that were open. All the rest of the file descriptors were closed. So that's a pretty cool way of doing it. Yeah, we had to fork the command 1025 times technically, but yep, that will totally work. Now, what we can do though, is instead of having to fork out to this command and let it take all this time, we can put this all in C and it will be a lot faster. So let's cp check fd.c to list fds.c. We're going to list all the file descriptors. This is super cool. So we're going to modify some stuff here. We're not going to take arguments. We don't need them. We are not going to take any arguments here. We're not going to do this. We are just going to simply do this. For int I equals 0, I less than 1024, I plus plus, do this. If the file descriptor is valid, so if fd valid of I, then we will printf fd open I, like this. Close that, close that. There you go. So we'll only print if the file descriptor is open, but we'll loop over all 1024 options. So let's cc list fds to list fds. There you go. Run list fds, and look at that. See how much faster that is? We know that 0, 1, and 2 are open, but the rest are closed. We could prove this. We could make 42 open to whatever standard out is, run this, and it will find that 42 is open. Like, hey, that's pretty cool. Run that, and it's gone. So that's all well and good, but you might be wondering, where does that 1024 come from? Well, I can show you. Since we're on Linux, we can do something pretty magical here. We can just proc sys fs file max, and this is how many file descriptors can be open on the entire box. That's pretty cool, but that doesn't really help us on a per process limit. So let's go ahead and look at this command that is built into bash called ulimit. Ulimit will tell us exactly that. Now, there are a lot of limits here. There are a lot of different limits on a per process thing that we can kind of look at, but the one that we're interested here is -n, maximum number of open file descriptors. So if we run ulimit -n, we can see that 1024 shows up. Now, here's the thing. There are soft limits and there are hard limits. There is a slight difference between the two. The soft limit is 1024. The hard limit is 4096. The soft limit is the one that's in effect, and we can modify the soft limit. The hard limit basically says, like, you can't really actually go above this. You might need like root privileges in order to do something like that. So you might think you could use sudo, but you're going to run into issues because it's a bash built in. I'll show you that though. We can do ulimit -a. Also, this is just good to know. Ulimit -a will show you all of the limits that you possibly have here, but I like ulimit -hn and ulimit -sn, which will show me the hard and the soft limits. We can modify these. I could set the soft limit to, let's say, 1023. I can lower it, and now the soft limit is set to 1023. The hard limit is still 4096. I could set the soft limit to 1025. Notice it was higher than it was before. That's fine because we're not going above the hard limit. If I were to set this to 4096, hey, that's totally fine. If I were to set this to 4097, nope, can't do that. We're trying to go above the hard limit. It won't work. Now be careful because the hard limit can also be modified. So the hard limit is currently 4096. That's totally fine. 4097, can't go above it. What if I set it to 4096? I just changed my hard limit. Okay, that's pretty cool. But, oh wait, no, 4096 is what it already was. I'm stupid. 4095. There we go. Like I said, you can't modify this. There's nothing we can do here. This is sort of given from on high. It looks like it's okay if I give it the limit it's already set to. That's so interesting. But yeah, it won't let me set it. You might think you can use sudo. Here's the thing, ulimit is not a command. It's built into bash, so it doesn't actually work that way. I would have to make a new bash shell with like root privileges, and then things might be slightly different. But for now, the hard limit is kind of given on high. But your soft limit, you are able to change. There are some weirdness around this. I also noticed that if I just manually set this to like 1023, I don't specify which limit. Take a look at this. If I look at the soft limit, it's 1023. If I look at the hard limit, it's also 1023. So be careful with this. You can actually kind of modify it, and you can get yourself into some really gnarly situations. Like if I were to say, hey, let's limit it to 3 file descriptors. Well, It actually just kicked me out of the server because there just wasn't enough for bash to work properly. So be careful with that. The nice thing is that shell's dead. We have the new shell here. So if I were to look at my limits again, they've been reset, which is super nice. So they're just for the duration of that bash process. I can type, I swear guys, I can type. There we go, 4096 and 1024. That's what I expect. Now we can get this information ourselves without having to use bash. We'll have the get r limit function that we can use. So you can see the C standard library here, include sysresource.h. There's a function called get r limit. You specify the resources you want and then the struct r limit. So this is just provided by this header for us. So the resource that we want is gonna be, I had to look this one up, r limit no file. So this specifies a value 1 greater than the maximum file descriptor number that can be opened by the process. So this is how we get those limits the way that they were being given to us from bash. So we could go ahead and we can modify our list FDs function. Oh, I'm not in that directory anymore because we got kicked out. That's funny. We can modify the list FDs function to, instead of hard coding 1024 here, we can call get our limit no file. And then we can give it a pointer to that struct. We have to actually create that. So struct r limit rl. There we go. We made a new struct. We ran it there. We have to pull in this header that it needed. So now this will have our limits there. There are two members of that struct. We can look at them here. We have an rlimt of current and max. This is just an unsigned integer type, so we can print it pretty easily. But rlim cur and rlim max. So cur is our soft and max is our hard limit. So we can just printf soft equals %u, hard equals %u because they're unsigned. New line, and then we have rl.rlim cur and rl.rlim max. There we go. Now that we have those two values, we can just swap this 1024 out with rl.rlim max. You could probably put the soft limit here. It probably doesn't make that much of a difference, but I would just put the maximum value here, and then we can loop over every possibility here. So let's go ahead, recompile that. Let's run list FDs, and there you go. We can see we have a soft limit of 1024. We have a hard limit of 4096. So we've looped all the way up to 4096 to see if the file descriptors were open. Hey, that's pretty cool. Now, if you remember, way earlier in the video, I said we could just ask the operating system because we're on Linux. You ready for this? ls/proc/$$ for our current PID/FD. There you go. There's our open file descriptors. See how much easier that is using Linux when we can just ask the kernel? That's awesome. Now, why is there 255 there? That's kind of weird. Let's do a long listing with human readable output. Okay, they all point to the same terminal, even 255 points to the terminal. That's a little bit odd. What's going on there? So an easy way to illustrate this is let's just change this to vim proc list FD. So we're gonna make a new program, proc list FDs. It's gonna be a bash script, so super simple. And it's just gonna ls-lh/proc/$$ That's all it's gonna do. Let's go ahead and give that the executable bit. Let's run proc list FDs and take a look at this. This points to proc list FDs. This is a bash thing. This is bash that does this. Bash opens up its own program that it's reading from because it needs to be able to read the data in the program. It's available as a file descriptor that's way up there, hopefully something that you'll never interact with. So file descriptor 255 in this case is the actual bash script itself. Super interesting, super weird. I actually learned that. I didn't even realize that was a thing. So as I was like writing down some notes for this video, I came across that. So that is pretty cool. Another thing we can do, we can totally switch gears, but we can use this trick now to our advantage is if we go back to one of the earlier programs from the beginning of the video, we have simple.c. So simple.c, and we do some stuff here. We open devfull, we write to it, and then we close it. Well, here's the beautiful thing. Once we open the file, we can actually just pause the program. Pause is just a simple function that will just stop the program from executing. So we'll open the file, and then we'll pause the program. So we'll cc simple out there. We'll run simple, and it will pause. All right. So I'm going to do Control Z to put it in the background, BG to run it in the background, echo $! to get the PID of the last program that was put in the background. And then we're going to ls proc that PID FD. And those are all the file descriptors open for the simple FD program. And as you can see, it has devfull open as file descriptor 3. So that's a pretty cool way of interrogating programs. Like if you're on Linux, other operating systems will have other things. I know Illumos also has the proc file system. You can look at /fd. Mac and FreeBSD won't exactly have that, but there are other tools. So yeah, this is just a cool trick to have under your belt, a cool thing to be able to see. Now we have to kill that program. So kill 17718. There we go. Let's just terminate that. There's no reason for that to be running. And finally, I want to show you one cool little like bonus trick. We're gonna do it in Bash. It could be very simple. Let's make a simple program called Spooky. All right, it's gonna be a little bit spooky, kind of a cute name. User bin env bash, and let's get that executable ready to run. It doesn't do anything right now. Let's go ahead and let's create a new file. So we'll do echo hello world, and we'll pipe that into foo.txt. Do we even have foo.txt? We don't have foo.txt. Perfect, perfect. That's good. That's what we want. We will echo hello world into foo.txt. And then we will open up a new file descriptor 3, for reading and writing to foo.txt. So we're gonna open this file up. That's really cool. We're gonna open this file up. Then we're going to delete it. So we're gonna open the file, we're gonna delete it, but then we are going to read from that file. So that file is deleted. In fact, we could even prove it. We could sleep for 2 seconds here. So we're going to write to the file. We're gonna open that file as file descriptor 3. We're gonna delete the file on the disk, but then we were gonna read from that open file descriptor. So it's not on the disk anymore, or it's not, the file path isn't on the disk, but we're reading from the open files descriptor, and it worked. We were able to read this data. This is a little bit spooky. I want you to think about the ramifications here. That means that a file can be open as a file descriptor, but not exist on your disk. Now the bytes have to be written somewhere, so they're probably written to your disk, but there's no file path. This is scary because, you know, like I've worked at companies where we've had like web servers. This was like a long time ago. We had Apache web servers, and they would be running to log files, and we would have programs that would come by and clean up those log files. They would delete those files. Apache still had them open. It was still logging to these files that existed as file descriptors, but they didn't exist on the disk as a file you could search for. This means we were running out of disk space, but we couldn't search for big files. Nothing was showing up. There were no big files on the disk. That was crazy. That was terrible. That's a nightmare to debug. So if you've ever been in this situation, you know exactly what I'm talking about. That sucks. So yeah, this can definitely be cool. I've seen people use this to write temporary files, delete the file immediately, but then keep the file descriptor around. I don't love it because as a system administrator, if I'm logging into that machine, I can't easily find the files that are taking up a lot of space. So it's a cool thing to be aware of. It's definitely a trick to be aware of. You'll have to spelunk through /proc to find these. Super annoying. That's a lot. I threw a lot at you. That's all I got for you. That is my deep dive into file descriptors. Hopefully these demystified a little bit about file descriptors for you. There's a lot going on. They're super interesting. I find them to be a ton of fun. And yeah, hopefully you guys enjoy. If you made it this far, dude, you guys are awesome. I appreciate you watching. Go ahead and hit the subscribe button, like the video, share it with your friends. And of course, we can't end a video without giving a shout out to my patrons over at Patreon. Thank you so much for your continued support. That script just hung for a while. I don't know what happened there. Normally it runs way faster than that. I'll have to look into that and see why it hung for like that shouldn't have that took too long to run. I wonder what's wrong there. Oh, beautiful. Thank you, Karen. That's awesome. So yeah, okay. I'll have to look into that. I think you guys are putting some weird characters in my program that I have to go through. But this is my favorite thing about the script that the Patreon users can change their names to. You guys can break it. I think that's a lot of fun. So I'm glad you guys are enjoying breaking the script. It's a ton of fun. I have a ton of fun making these videos, and I love that you guys support me on Patreon. I think that's super cool. Thank you so much for your continued support, guys. It's awesome. I appreciate it. Oh man, I totally just realized I didn't have the newest script. I made some modifications to the script, I just realized. Oh, that's so lame. Yeah, I made some modifications. Okay. Yeah, you know what I'm thinking? I'm thinking it had to recompile the Rust program, and that's why it took so long to run to begin with. Yeah, I made a modification. When it gets to the bottom of the script, I've added more metadata. I got a comment from someone on the YouTube comment, and they were like, hey, you should put things like your sub count and stuff at the bottom of the script. So I went ahead and added that. But yeah, again, I'm just reiterating this, and I'm just totally repeating myself. Thank you guys so much for watching. I appreciate it. All this code will be online. I'll have a link below. Like, comment, subscribe, all that stuff. Let me know what you guys think about this kind of video. And yeah, that's all I got from it. Thank you, everyone. I'll see you later. Have a good night. Take care. Oh, I said all that, but now I gotta watch it. Yeah, look at that. Beautiful. Beautiful. That's awesome. All right, now I'm really leaving. See ya.